now that you understand the basic idea of cluster analysis, what we are trying to do with cluster analysis, let's take a look at one common technique for performing cluster analysis. There are many techniques for performing cluster analysis. The k-means clustering method is one of the commonly used methods. So let's try to understand that. But of course, like in k-means clustering, what happens is you first choose a value of k. And then you say, I'm going to break the data into k clusters in such a way that each cluster is as coherent as possible. Okay, so that's the idea of how k-means clustering works. So you first pick a value of k and then you break the data into k clusters in the best possible way. Okay, of course the question is, how do you know what the value of k should be? And the answer to that question is, we've already seen it very briefly earlier, that you try different values of k and find out which one provides you the best benefit in terms of reduction of overall sum of squares, adding up of all the within sum of squares, right? So you'll find that at some level you get a maximum reduction, and then the reduction in error kind of tapers off. Of course, you do keep on getting improvements as you have more clusters, but the improvements are not very valuable, right? So you use that criterion as we'd seen before and as we'll see again. Okay, so let's understand how k-means clustering works. Again, I'm taking data in 2 dimensions so that we can visualize it. So the points are all the points that are shown. In k-means clustering, what the system does is it first selects k points. In other words, in this case, k equals 5. So it has selected 5 points, 1, 2, 3, 4, 5, randomly as to act as centers of the clusters. Okay, it's a complete random selection. And then what it does is it assigns every data point to one of these 5 points based on whichever is the closest. Okay, so for example, you've got all of these points would be assigned to this guy because they're all closest to this point. Perhaps all of these would also be assigned to this because all of these are closest to this one. All of these will probably be will definitely be assigned to this because this is the one to which they are all closest, and so on and so on. Okay, it's going to do that for every single point. Once it does that, what you're going to have is you're going to have some points associated with this center, some points associated with this, some points, etc., etc. And then what it's going to do is to recalculate the average, right? So you've got, let's say, 25 points are closest to this guy. Okay, then what it's going to do is it's going to take the 25 points which are closest to this, and it's going to calculate the midpoint of that cluster, right? So tentatively, you have the data broken up into 5 clusters simply in terms of the points being assigned to each of those. But it's not going to leave it there because that may not be a good solution. That was just a random solution. It's going to recalculate the cluster center for each cluster. Okay, and then it's going to repeat the process of finding which point is now closest to each of those points, right? And it's going to keep on doing this repeatedly until after some time what will happen is that no points will get reassigned. The clusters will stabilize. Okay, and that's the clustering solution for that given value of k, right? So here, after the first round, what it's going to do is it's going to assign the points to each of these cluster centers, and it's going to recalculate the cluster centers. What happens is you get this. Okay, so you've got one cluster center has moved down here. Okay, it's gone from here, it's moved down here. Another cluster center has moved here, right? So you've got the 5 cluster centers reassigned. There's one sitting right in the middle of that. 1, 2, 3, 4, 5. These 3, 4, and 5. Okay, so the cluster centers have moved a little bit closer. Like for example, see here, this one moved between these 2. Okay, and then it's going to repeat that same process once again. This is what we saw in the previous page on the second side, and things move again. Okay, so now what you see is there's one point right bang in the middle here, right? So this one has come closer to this, and you've got those 2. And then this process continues repeating. Okay, so now you see one point is moved right down here, another point is moved here, right? And then you've got this point sort of assigned to all of these clusters. Okay, so what has happened is you've got a cluster consisting of these points, another one of these, another one of these, and then you've got these two clusters taking care of all these widely distributed points. Okay, now you can see that now things are not changing at all. It's almost identical. In fact, I think it has become completely identical. At this point, there's no change, and then the system stops and say, okay, these are your five clusters. So this is one cluster, 2, 3, 4, 5 clusters. Okay. Now, if you had said 6, then the solution would have been different. If you had said 4, the solution would still have been different. Okay, so you can see that things are now completely stable. There's no change. This is the final clustering solution for k equal to 5 for this set of points. Here we've taken k equal to 6 for the same set of points. Okay, and again, initially it randomly put up the points. This time it put them here. Okay, and the final one turns out to be this. Notice how it identifies the clusters pretty well. Okay, just through a mechanical process of adopting this k-means clustering approach. Here's an example, same points again. This is a different set of points. This time I've chosen the points to be quite well distributed, and I choose k equals 4, and you get this as the final clustering solution. Okay, so you can see here that it makes sense to have a cluster centered around here, another cluster centered around there, one here, and these points are not very close, so therefore you've got a fairly heterogeneous cluster sitting here. Okay, so that's how k-means clustering works. So how do we select a good value for k? Now this is the diagram that shows you the total of the within SS for all the clusters. Right? This is a diagram we've seen before. So that's the case when all the points are in one cluster, and we got the total SS as 22, right? Because all the points are in one cluster. You calculate its within sum of squares, you get 22. Okay, so that's what you see here. The moment you go to two clusters, you see a phenomenal drop in the total of the within SS because you've got two extremely coherent clusters, and therefore within each cluster there's not much of a deviation from the mean as compared to the original situation, right? But if you go from 2 clusters to 3 clusters, you're still seeing an improvement, but it's not much. Again, the drops are not at all significant, right? Now, this is a graph which will help us to make a decision on what value of k we prefer, right? So it's a completely subjective decision. You may say, well, I would prefer to have, as low an error as I can get. And so you may say, well, even here there's quite a big drop, so I'm going to choose this. Well, that's a subjective decision, but beyond this point, there's absolutely no improvement. There's no reason to go beyond 6 clusters, but even 6 clusters is not meaningful here. So I would probably say 2 seems to be a good solution for this scenario. Okay, but of course, this is based on a data set that I hand created. But in a real data set also, you'll see this kind of a scenario, and we'll see examples of that later on.